All right, so this is part 2 of our Chapter 16 lecture on thermodynamics, entropy, free energy, and equilibrium. So continuing on where we left off, we're looking at standard molar entropies and entropies of reaction, right? So we can define this entropy of particular materials at a given temperature, pressure condition with this standard molar entropy, right? So it's the entropy of 1 mole of a pure substance at 1 atmosphere and a specified temperature, usually 25. I like how the text points this out because different books and different indices will have different temperatures under certain instances. Again, we notice this little degree sign here. That's our naught sign, so this is S naught for the standard molar entropy. And it's usually 25 degrees Celsius for these, but be aware that some books or some appendices or some resources might have it at 0, and you will need to make an adjustment or find a correct one to make sure that everything matches up for whatever you're working on or doing. The units of S naught are joules per Kelvin mole. We've seen before that the typical units of entropy are joules Kelvin. Standard molar entropies are often called absolute entropies because they're measured with respect to an absolute reference point, the entropy of a perfectly ordered crystalline substance at 0 Kelvin. Not all thermodynamic parameters have a clear absolute as clearly as this, but entropy definitely does. And this is why, as we'll go forward, that unlike for delta H, for formation, where like we have to say that like something in its elemental state is 0, for entropy we can actually define what entropy is for pretty much everything across the board. So they show here that even like oxygen gas at 25 degrees has an entropy, unlike the case for enthalpy and as we'll see for Gibbs free energy as well. So we can calculate the change in entropy by calculating the entropy of formation of the products minus the entropy of formation for the reactants. This products minus reactants setup. We'll multiply each one of them by their respective coefficients in a balanced equation, and we can perform this calculation. Now, this calculation is fairly tedious, so I generally don't ask for it on exams, but you will have problems in which you will need to use it in order to understand how to use reference materials. Generally speaking, when you're working with values like this, you're looking things up in a table or having reference materials. You do not need to memorize any entropy values for anything across the board. These are ones that you will look up in the text as you need them or from various appendices as you're working through problems. Or they'll be provided to you in some way, shape, or form. So as you'll see here, the S naught values are quoted on a per mole basis, so we have to use the molar coefficients as we plug into our equation to calculate the change in molar entropy here. Again, that's a S naught because we're under some standard conditions here, and in the equation, the units of the coefficients are moles, so the value of delta S here is just in joules Kelvin, which is the typical unit for changes in entropy or for entropy more broadly. So they work this out and they find the value here for this particular change by looking values up in a table. We expect an increase in entropy whenever a molecule breaks into 2 or more pieces. Keep that in mind as well. So calculating the standard entropy of a reaction. So here they have the Haber synthesis of ammonia, and to calculate this change in standard molar entropy, the values are looked up in a text, plugged in, multiplied by their respective coefficients, products minus reactants, added up as well in here, and a value can be calculated. We know that this number should be negative because we're reducing the number of gaseous moles, so that's an expectation we should have for our answer. We can use those qualitative ideas to get a sense of where our quantitative number should come out, like relative to something else or something else in a problem or somewhere else. Keep that in your mind because that will help you check against math errors, especially sign errors, which can be common in these contexts as well. Entropy and the second law of thermodynamics, right? So the first law of thermodynamics states that in any process, spontaneous or non-spontaneous, the total energy of a system and its surroundings is constant. But for the second law, in any spontaneous process, the total entropy of a system and its surroundings must always increase. And they talk here again about this idea of a free energy, right? And an equation that we'll delve into in a little more detail. If this free energy change, that's this delta G here, is less than 0, then the reaction is spontaneous because free energy was consumed in the process. If it's greater, then the reaction is non-spontaneous because free energy had to be put in. And if it's 0, then the reaction is at equilibrium and no change from a thermodynamic standpoint occurred. Remember that a system in equilibrium can't do anything from a thermodynamic standpoint. Things are still happening inside it, Things are still interconverting. There's still things going on in it, but no net change occurs, so I can't measure anything from a thermodynamic standpoint. So the first law is simply a statement of conservation of energy. In an exothermic reaction, the system loses heat or enthalpy to the surroundings. In an endothermic one, the system gains enthalpy or heat from the surroundings. Because energy is conserved in all chemical processes, spontaneous and non-spontaneous, the first law helps us keep track of energy flow between the system and the surroundings, but it doesn't tell us whether a particular reaction will be spontaneous or non-spontaneous. The second law, however, provides a clear-cut distinction for spontaneity. It says the direction of a spontaneous change is always determined by the sign of the total entropy change. Sometimes they call this total entropy change the change in entropy of the universe. So keep that in mind also if you've seen that before in other texts. If the total entropy change is greater than 0, then this reaction is spontaneous. If it's less than 0, then the reaction is non-spontaneous. If it's equal to 0, then the reaction mixture is at equilibrium. So all reactions proceed spontaneously in the direction that increases entropy of the system plus surroundings, or as they say, the universe. Now, keep in mind that there's no entropy change if the system is at equilibrium already, and that's interesting, right? Because we can imagine that we kind of lose energy to heat and to entropy that we can't get back when we perform certain processes, right? So if we make sure a process is spontaneous, we'll always be losing some of its energy or efficiency or something to this delta S total, to this change in entropy of the universe in order for the process to happen, right? So there's an idea that if we can perform a reaction close to equilibrium, then we can minimize this. We can bring this delta S total down or closer to 0, right? And that is true. If a reaction is performed close to equilibrium but not quite at equilibrium so the change can still occur, generally speaking, it results in a higher efficiency. And you get more energy as work and you get other stuff, but you also have a slower reaction. So it takes longer to obtain that energy. So there's a trade-off going on there, but in general, if reactions are done closer to equilibrium, you can increase the efficiency of the process. And some systems, like in living systems, chemical systems that they use, do occur close to equilibrium for these purposes in order to minimize losses and to minimize entropy. So this is something to also keep in mind, that reactions close to equilibrium can try to minimize the entropy change in the universe. We also get a nice equation here for the change in entropy of the surroundings, that's simply the enthalpy change or the change in heat. So if something's exothermic, this is negative with a negative sign in front of it, which makes it positive so that the surroundings increase in entropy. If this is positive, then this sign makes it negative so that the system can take energy take entropy from the surroundings, and so that the surroundings can decrease in entropy if they lose heat into the system. So this is a very useful equation. And everything is always at some constant temperature T. So they say here, we won't derive this, we can justify its form. We can see that delta S of surroundings is proportional to negative delta H, because in an exothermic reaction, the system loses heat, so the random motion increases and the entropy of the surroundings increases. But if it's endothermic, then the system gains heat from the surroundings and the entropy of the surroundings therefore decreases. So keep this in mind. Useful equation because it gives us an easy way to calculate this, which sometimes can be difficult to estimate entropy changes otherwise. So if the system gives off heat, the surroundings entropy increases. If the system withdraws heat from the surroundings, then the entropy of the surroundings decreases. We can imagine that delta S surroundings is inversely proportional to temperature by imagining that it's in some large container bath with heat can be added without changing temperature. There's a whole thing about this, but in any case, the idea is that we can see whether a certain amount of heat being put into the system allows greater access to modalities, like I was talking about before. The reason that the increased temperature increases entropy is that it allows access to more modalities. Well, that's proportional to temperature. So as the temperature increases, it takes more energy to access additional modalities for the particles. So overall, you get more entropy increase with a given amount of heat at a lower temperature than at a higher temperature. And they talk a little bit more about this. It's like a contribution to a stack, or like a pebble in a choppy surface or a smooth surface, how much it contributes to the choppiness. Interesting, but not really something particularly testable here. So they look at the oxidation of a metal, and they want us to see look at the sign of delta S total. Well, we'd have to go to some tables to get values for this. This problem kind of stands out, but it doesn't really give us a lot of information. So to get delta S for this system, we can use delta S naught because they told us that we're at 25 degrees Celsius, and we're going to assume we're at 1 atmosphere, and we're going to assume all those other conditions are true, so we can get a value for delta S of the system using the sum of the products minus the reactants process. Similarly, we get delta H. They look those up in the appendix and get values for this. 0 for elements in their standard state given the temperature. So like gaseous oxygen at 25 degrees Celsius has 0 enthalpy, but it would have something if it was a liquid or a solid. Similarly for the solid iron, it's the state it would be in at 25 for enthalpies. So they plug that in and they're able to calculate a value. Then they're able to use the surroundings calculation that we just looked at to estimate a value for the change in the entropy of the surroundings. Again, sometimes they put a plus sign in front of these and sometimes they don't. And then they're able to sum these up because it turns out that the entropy for the system actually decreases in this process, and that makes sense. We lose 3 moles of gas in this process, so that actually makes some sense. The system, though, this process is spontaneous, and by looking this up, we see that it's highly exothermic. So we're able to do this sum and get an overall value for the change in entropy of the universe. Oxidation of metals is generally exothermic, so that gives us a sense that makes sense from our understanding as well. So free energy and spontaneity. So the value G is related to free energy, right? We've kind of seen that a little bit before. It was named after Willard Gibbs. And the free energy G of the system is defined as the free energy equals the enthalpy minus temperature times the entropy. Now, generally, we're looking at this in context of changes, so this free energy change equation down here at the bottom is super, super important. Delta G equals delta H minus T delta S. Keep this equation in mind. You will need it a lot to work out a variety of different kinds of problems that seem very complex, but they actually can kind of reduce down to this. So if we look at this in terms of the delta S total, we can break this down and replace the components in here with the definition of the enthalpy change of the surroundings, multiply everything by negative T. And it turns out that delta G is actually equal to negative T delta S of the universe is delta G. So another way to think about delta G, otherwise being in terms of a maximum amount of work, another way to think about it is the negative of the temperature times the change in entropy for the universe. Another way to think about it, G as free energy can be thought of as both of those. So because it's a unit of energy, not a unit of joules over some temperature. So this converts this into a unit of energy. And that delta G and entropy have opposite signs. And absolute temperature Kelvin is always positive. So if delta G is negative, then the reaction is spontaneous. If delta G is positive, then the reaction is non-spontaneous. And if delta G is 0, then the reaction mixture is at equilibrium. Any spontaneous process at constant temperature and pressure, the free energy of the system always decreases. Keep that in mind. This table here will be extremely helpful to you. You should, in fact, write this one down, keep it on a flashcard, make note of it, particularly for your review, because you will have problems based on this on an exam. So delta H, when delta H is negative, delta S is positive, that results in a delta G that is always negative. If you look here at the problem, if delta S is positive, then this number here will always be negative, and this number is always negative. So that means delta G is always negative, resulting in a spontaneity at all temperatures result. Similarly, if these are reversed, if delta H is positive and delta S is negative, then delta G will always be positive, and we'll see non-spontaneous at all temperatures. In the other two conditions, temperature will control the spontaneity of the system. And this makes sense because this is kind of connected to what we already understand with K. So some systems will be spontaneous at low temperatures, but non-spontaneous at higher ones, and others will be vice versa. And it'll depend on what these signs are. If you remember this, you'll get kind of a shortcut into figuring out, just based on the relative values of things, where the spontaneity should go and where the spontaneity should be. And you can calculate these changes in these kind of fallover points, right? These changeover points can be used to estimate things like boiling points or places where K will change from something greater than 1 to something less than 1 as the system reverses direction. They give us an equation here for this crossover temperature for systems where you have those the signs line up in such a way that that's an idea. And this gives you an estimate because, of course, delta H and delta S are somewhat dependent on temperature. They say somewhat in the book. That's a bit of an overestimation. They're quite dependent on temperature in certain contexts, but for the most part, for reactions near or around room temperature, they generally don't change that much with temperature. As a result, values for this reaction are relatively independent over a small temperature range, like room temperature to like 30 degrees and something like that, like in that sort of range, human tolerable temperatures. So iron metal can be produced by reducing iron 3 oxide with hydrogen. And they ask us here, is this reaction spontaneous under standard state conditions? So they calculate delta G for the reaction by looking up the value. Well, they got the values. They provided them here for us. So they were able to just plug these values right in and calculate delta G is a positive number, so that means it's non-spontaneous at a 298 or 25 degrees Celsius. They say at what temperature will it become spontaneous? They use their little equation here to estimate that, and they get 698 Kelvin. You could convert this to Celsius depending on what the problem is. Often in a problem like this, they'll want you to convert it to Celsius, subtract 273.15, remember, and you can get the Celsius temperature. Because the standard state, these values are unchanged. This is an estimate, but that's really all you'll need for questions like this. Continuing along with standard free energy change, right? Remember that the standard state requires solids, liquids, and gases to be in their pure forms at 1 atmosphere of pressure, solutes at 1 molar concentration, and a specified temperature, usually 25 degrees Celsius. This is the same standard state that we've seen before, and these standard state conditions will apply to everything in this chapter as well as subsequent chapters where we'll see this little degree sign repeating ourselves again. But we just want to make a note because it's really important to keep that distinction in mind between the versions that have these little degree signs and the versions that don't. It radically changes the meaning of the value because this is under standard state conditions, whereas when this is not here, that means it's under the true conditions, whatever we actually did. We'll see that distinction come up in more detail going forward. So they show here calculating the standard free energy change, and you can see that the reaction is spontaneous because this value is negative. They say it's important to note that the standard free energy change applies to a hypothetical process rather than an actual one. In the hypothetical process, separate reactants in their standard state are completely converted to separate products. In an actual process, they may not be going to completion, so we may not exactly know. So there's more here to keep in mind. They show here in the Haber process, the hypothetical process is this. The reactants are not separate but are mixed together. And moreover, the reaction doesn't go to completion. It reaches an equilibrium state in which they're both present together. So we don't see this value necessarily appearing in real life. It just gives us a sense of what it would be if we could do that. Now we're imagining this real process. They say here that the free energy change for this process is the standard free energy change, delta G, because each reactant is present in 1 pressure. And again, as always, the value of delta G naught indicates only whether the reaction is spontaneous, but doesn't provide anything about the rate. So again, we're thinking about more hypothetical situations and remembering that delta G doesn't really tell us anything about the rate. So we're going to calculate the standard free energy changes. They use the values from the appendix. They calculate a value for delta H naught from values provided in an appendix and delta S naught from a value provided in an appendix. Plug them in, and then they're able to obtain a value for delta G naught. This is one way to do it. There are other appendices that will actually give you the delta G values, so you can do a final minus initial with delta G itself. Remembering the delta G follows the delta H rules, where pure substances like the iron in the solid state at their correct phase for the given temperature will have a value of 0 for the enthalpy. They'll also have a value of 0 for their Gibbs free energy. So they say, is this reaction spontaneous or non-spontaneous? So it's negative, so that'll mean that it is spontaneous. Then that means it will move forward in the forward direction. That the reverse reaction becomes spontaneous at high temperatures. So if we look at this, then as we increase this value, we'll see that this is not negative. And if we look back at our chart, as this temperature becomes bigger, this just gets more negative over here. There's never any kind of sign flipping going on. You've got the condition where delta H is negative and delta S is positive. So the forward reaction is spontaneous at all temperatures, and the backward reaction never becomes spontaneous. So let's take a look at the standard free energy of formation, right? And again, we can look these up in a textbook, and this may provide a shortcut so we don't have to use the delta H and delta S on every single step. And we see that involved here. Sometimes we'll just simply be provided with it for a given reaction at a given temperature condition. And they show that we can look these up in a text. Notice that graphite is 0. Graphite's the phase for carbon. Diamond is not. Diamonds are spontaneously turning into graphite over time. It's just really, really slow, right? Hydrogen is in its correct elemental state. Nitrogen is in its correct elemental state. So we see that this follows the delta H rules. We only need a free energy difference. Again, that's why we don't have a good sea level like we do for entropy. Substances that have a positive value for the delta G of formation, such as ethylene and nitrogen dioxide, are thermodynamically unstable with respect to their constituent elements and can, in fact, decompose. But those that have a negative value for delta G of formation are stable and do not decompose under standard state conditions. They may under other conditions. Given enough heat, pressure, and other conditions, things can become stable that weren't stable, or vice versa. So keep that in mind. It is always temperature dependent. So they plug in the standard free energy change, and again, this works the same way as delta H like we talked about. So they compare the values that you could get from doing the full equation out, the Gibbs equation here out, compared to the Gibbs energy calculated from references, and you get a very close value. So you can use that also. And this is the text showing you how to do that, in addition, showing you another way to obtain this. They say, is it worth trying to find a catalyst for this reaction? Well, I can only find a catalyst for a reaction if the forward reaction is already favored, if that's what I want to do. If the backward reaction was favored, then no catalyst is going to allow me to turn the reaction around. Catalysts can only increase the speed. They can't change the thermodynamic condition, right? So if delta G is negative, then it's worth finding a catalyst to make that go faster. But if delta G was positive, then it would not be. It's not worth finding a catalyst for this other reaction because that would mean that it would be positive, and a catalyst can only increase the rate of decomposition. It would not be able to reverse the direction of the reaction. So now we finally get to free energy changes for reactions under non-standard state conditions. So this is the relationship between the standard state and the real state. So this delta G with no naught, with no little circle, is the real delta G under whatever conditions are present in Q and whatever temperature is plugged in here. This delta G is the standard state delta G. So basically we're calculating like a deviation from the standard state to account for our real state, and then getting a real delta G for the real process that we might actually do that doesn't have to follow all these standard state pressure and other kinds of conditions. But we're using delta G still as a reference. Keep in mind these two delta Gs are two different delta Gs, even though they look very similar. So to calculate the real free energy change, we'll have to calculate the value of Q, which we'll need all these concentrations to do. We do that. We plug that in. We're able to get this delta G naught from some reference table, and then we're able to calculate a value for real delta G under these given conditions. And that allows me to actually see that the real free energy change here would be negative, so that would mean that the system would move in the forward direction, right? And delta G naught here is more positive than delta G, the real delta G, because Q is less than 1. So keep in mind that the reaction has a greater thermodynamic tendency to occur under decided conditions than under standard state conditions. Sometimes these can be entirely different. Sometimes delta G naught can be a positive number, and then delta G can be a negative number. These things can happen depending on how the conditions are changed, right? For example, in this one, delta G naught is a negative number, but delta G here is a positive number. Q is large enough to give a positive value for delta G, so the reaction is non-spontaneous and reverses itself. Okay. So free energy changes in equilibrium. So here's where we're going to get into the fundamental connection between delta G and K. So we see here that delta G equals delta G naught plus RT ln Q, like we looked at for the example. And remember that this R is the R that's in joules, the 8.3145 one, not the 0.082057 because we need to make sure everything here is in joules. When a reaction mixture is mostly reactants, Q is less than 1, RT ln Q is less than 1, and G is negative, delta G is negative, so the reaction can form some products. In the reverse, then the reaction will reverse itself and delta G will be positive. So they talk here about spontaneous and non-spontaneous reactions moving toward an equilibrium where delta G is 0, where there's no change in G, and where we've minimized the reactant versus product energy situation here. So here's the next fundamental equation, right? So what happens if Q happened to be K? If our current arrangement happened to be at equilibrium? Well, that would mean that delta G would be 0, because delta G is 0 at equilibrium. So we plug that in, so we can rearrange it to this equation. This is a very important equation, and it relates delta G at our standard state conditions to RT times the natural log of the equilibrium constant. So if we can get the equilibrium constant, then we can obtain this value for delta G naught. And this is a really, really critical relationship, because sometimes it's hard to measure one or the other. But if you can measure K, you can get the change in the standard state Gibbs free energy, and vice versa. Sometimes it's easier to measure this energy and then to derive a value for K. Both of them can be difficult to obtain in certain conditions. And that's what they talk about here. This is like the most important relationship in this chapter, probably after that Gibbs equation, because it allows us to actually relate something that we can measure, one or the other, to something that might be really difficult to measure under certain conditions. Oftentimes we can't measure K very easily, but we can get delta G naught from a reference, which can be obtained from delta H and delta S metrics, which we've seen how to calculate other ways and how we might measure that empirically. So if delta G naught is less than 0, then the natural log of K is greater than 0 and K is greater than 1. So if delta G naught is a negative number, then K is greater than 1 under the 25-degree temperature kind of setup. If delta G naught is greater than 0, then K is less than 1. If delta G naught is 0, then K is equal to 1. This just doesn't happen very often, but generally really small values for delta G naught indicate a K where there's a lot of both reactants and products. But larger values, very negative values, indicate a very large value for K. Very positive values indicate a very small value for K. Just keep all this in mind. So now we've answered some of the more fundamental questions in this chapter. We can now understand that the equilibrium constant and the Gibbs free energy are very tightly related. And one way to understand the equilibrium system is in terms of the standard free energy change. And vice versa. We can understand both of them in terms of the other, depending on what the system, which makes more sense in terms of the system and its processes. So we can calculate an equilibrium constant from delta G naught, and they show how this would be done using the equations we obtained, and they look up the values in a table and they calculate the value for delta G naught. Now in here, they take the anti-natural log e to the 10.1. Now, depending on how big this number ends up being, some calculators won't be able to obtain this, so you may have to leave your values in terms of e raised to some large power, and that'll be acceptable on a test if that's beyond the realm of a calculator to obtain. As it's true under certain conditions, these numbers just get really, really huge, because you might have a very large K value, because you have an extremely negative delta G naught for this particular setup. So, okay, so let's take a look finally at kind of a little more of the concepts involved in entropy, right? Entropy can be said to, in some ways, be one of the time arrows. Like spontaneous processes, which include things even beyond chemical systems, always increase entropy. They go in the direction of the thing most likely, right? And in one way, we can use that to define, to distinguish between the past and the present, or the present and the future, because future states will have more entropy than past states by definition, right? And it also kind of conceptually gives us one, right? Because while we can look at like what the most likely state would be, it's hard to then turn around and go backward and figure out which unlikely state we came from. Entropy seems to be a tendency of taking less likely states and bringing them toward more likely states, but not the reverse. So that helps give us some kind of directionality to time itself, right? The reverse process would have to go backward in time, and it would decrease the entropy of the universe. So it gives us sort of one-way nature to time that isn't shared by other quantities. Another thing to consider is systems that decrease in entropy, right? Like when crystals form as they fall out of solution, or as cells grow and reproduce, they have to maintain areas of low entropy relative to other areas, or they are able to incorporate additional information from their surroundings or other things like that that lead to a so-called increased order. This is actually totally fine from a thermodynamic standpoint, because as we've seen, we just need the system plus the surroundings to increase in entropy, or the universe to increase in entropy. Local decreases in entropy happen all the time, like the ice freezing in the freezer. So local decreases in entropy are totally fine, even for living systems. And in some ways, there are some models of the universe in which life is a mechanism for actually increasing the entropy of the universe, because the activities of these organisms actually end up spreading out all kinds of energy into a variety of different forms as they take in chemical or photo energy from the sun or from other places and convert it into all kinds of different random motion all over the planet and scatter it all into all different forms. That in some ways that can be thought of as an entropy increasing like system. You know, a lot of people, they think about life and how it seems to rely on keeping low disorder, right, in certain places in order for like a cell to live. But really, when you kind of zoom out, you can see that really it works like any kind of chemical process from a thermodynamic standpoint. And as long as we see an increase in entropy for all of those processes, there's nothing forbidden. We're taking all of this solar energy that's all in one form and breaking it up into a variety of different chemical and motion energies and all kinds of different things. So they say here, thus, an organism pays for its decrease in entropy by increasing the entropy of the rest of the universe. So there you go. All right, well, thank you for coming on this journey with me, going through this chapter. I will see you all in the next chapter, and I hope this was very edifying for you. Have a great rest of your day, and thank you so much. Bye-bye.